Yeah. Mhm.
Okay. Well, today Dr. was going to present the most recent uh, version of this paper. Um, I think there were some substantial changes from the last time we sort of saw your first draft. So I look forward to hearing where you've gone with that.
Okay, well, I can, I did prepare a couple of pages that then I will use the revision paper. There are some problems I have I'd like to talk about and show you where I'm at. I think the ideas are very interesting, but well, like I say, I like to share. Uh, so if you like, I can maybe share screen right away and try to get it to work.
Sure, yeah, go right ahead.
Okay, so I can do this here. Can you see that or not?
Not yet.
Not yet. Okay, let's see if I can get it to work right here. Okay, I'm trying to share screen here. Oh, okay, here I guess.
Yes, that looks good.
Okay, good. So yeah, I'm not going to have so much trouble. I can. Okay, let's see if I can make it wider here. How's that?
That's just fine for me. Yeah.
Yes.
Okay, so I like to start. Well, you've seen this material before, but it is important. So again, this is a way of writing a basis of a 2x2 matrix algebra in terms of these null vectors A and B. In particular, I'm interested in the sequence of geometric algebras G11, G12, and G22. Okay, because this G11 and G12 can all be represented in terms of 2x2 matrices, whereas when you step to G22, then you have to go to 4x4 matrices to get a representation of it. Okay, so these are the usual rules here that we've talked about before. Namely, A and B are idempotents. Well, no, nilpotents. They're vectors, and they have square 0. And of course, for the two-dimensional case, we have this relationship AB plus BA is equal to 1. Well, once we establish those rules, then we have this multiplication table, which I've shown you on various occasions. So we define now the vectors E1 equal to A1 plus B1 and F1 equal to A1 minus B1. And they define a basis of the geometric algebra G11, because E1 squared, if you're just using these rules here, we find that E1 squared is equal to 1 and F1 squared is equal to minus 1. Very simple calculations. But also notice that if we multiply E1 times E2 using these rules here, we get it equal to, well, you can see A1 minus B1. We have A1 wedge B1 minus B1 wedge A1. Okay, so you get 2A1 wedge B1. Well, okay, so the matrix representation then of E1 and F1, 2x2 matrix representation are just E1 equal to 1, 1, and F1 is equal to 1 minus 1. Well, you see, when we go to the Pauli algebra, we just multiply F1 times I, and we get minus I and I if we wanted to go to the geometric algebra G3. Okay, let's go to the next page. So again, the idempotents A1, or the nilpotents A1 and B1 are just A1 is equal to 1, 0, 0, 0. B1 is equal to 0, 0, 0, 1. Of course, you can see that those matrices have square one. So they're just, that's a matrix representation of the geometric algebra G11.
Square zero, yeah.
Okay, so now I'd like to generalize those ideas to apply to any number of nilpotents. So instead of using A1 and B1, I'm going to use A1 and A2. I'm also not going to make it boldface anymore because I haven't used boldface here then. So again, we think about the generalization I'm looking for is we want to pick out A1. These are null vectors. They all have square zero. So we have A1 has square zero, A2, which is the same thing as B1. I'm just replacing the notation to use only using the A's now. So we have A1 up to AN. That's in this general symplectic, if you want to call it, n-dimensional simplex defined by what I'm thinking about these null vectors, A1 up to AN. Okay, so let's look at the simplest case. So the simplest case again is what I call S2, A1, A2. So we have two nilpotents, null vectors that have square zero. We also define this new constant, which I call rho 2 in this case, because we have two null vectors, A1 and A2. They have square zero, and I define rho 2 to be the constant 1 over 2 to the 2 minus 1. So again, that's just 1/2. Well, you can see when we said here that AB plus BA is equal to 1 in geometric algebra, AB plus BA is equal to 2A dot B. So we're taking the dot product, the inner product of the null vectors A and B. AB plus BA is equal to 2A dot B. So that's why I have the rule then in this first case that A1 dot A2 is equal to 1/2 times the delta symbol ij. Of course, if I is equal to j, then we just get 1/2. So it agrees then with what I previously wrote down for the A and B. And also, we said that A wedge B is not equal to 0. Now that translates to A1 wedge A2 is not equal to 0 then. Okay, so now we go to the next interesting case that we know about, and that's what I call the 3 simplex plus. I use this plus sign only because I'm defining the inner product of these null vectors to be 1 over 2 to the n minus 1. So in this case, row 3 for 3 null vectors is 1 over 2 to the 3 minus 1, or 1 over 2 squared is 1/4. Okay, so I want to choose these null vectors such that A1 dot A2, A2 dot A3, A1 dot A3, they're all equal to 1/4. And again, we have the condition that should be an A1 wedge A2, wedge A3 is not equal to 0. So this should be an A here. Okay, now, so I want to identify that with the geometric
Just
algebra.
one question.
Yeah.
Just a question here. You're missing a delta symbol there on the last expression.
Oh, yeah, that's true. That's true. It should be dealt just like here.
Yeah. Mm-hmm.
Yeah, that's correct. Yeah, so that should be a delta there. Okay, so the geometric algebra G12 is defined by three vectors. Well, we call that a Euclidean vector because E1 squared is equal to 1, and 2 pseudo-Euclidean vectors, which have square -1, and they all anti-commute. Okay, now I claim, well, I want to construct that these three vectors, E1, E2, and F2, in terms of these three null vectors, which have square 0. Okay, I call that A1, A2, and A3. And here's how we define it. We can define, so usually we call this the standard basis of the geometric algebra 1, 2. We have E1 squared equal to 1, F1 squared equal to -1, F2 squared equal to -1, and the anti-commute. That defines the geometric algebra G1, 2. Okay, so now we can relate the A's directly to the standard basis of this geometric algebra. So we define A1 equal to E1 plus F1, A2 is equal to E1 minus F1, and A3 is equal to E1 plus F2. Okay, now if we calculate the matrices of these things, remember now that E1 and F1 are the same thing as what we had E1 and F1 here, the same, exactly the same, except I'm not using boldface. Okay, so we substitute in the matrices, take the matrix of A1, it's just the sum of the matrix of E1 plus F1. Okay, so here's the matrix of, if you calculate it out, what we get is a matrix of A1 is 1 over the square root of 2, 0, 0, 1, 0. Well, not surprising, all we've done is change the denominator of this thing by a factor of the square root of 2. A2, well, that's the same thing as the B. That was the same as the B. Now notice now I look at this trivector I. I is equal to E1 times F1 times F2. That's a trivector in this geometric algebra G1, 2 here. And if you square that, it's not difficult to see that I squared, well, you can see F2 will anti-commute with F1 and E1. So in E1 times F1, that has square plus 1. F2 has square minus 1. So I squared is equal to -1. It's also in the center of this geometric algebra. It commutes with all these what's in the center of the geometric algebra G1, 2. I commutes with E1, F1, and F2. Okay, so okay, now the question is, what is the matrix of F2? Well, okay, here we have it. We first of all solve this equation for F. If I is equal to E1 times F1 times F2, then all we have to do is multiply E1 times F1 to both sides of this equation, and we get F2 is equal to E1 times F1 times I. Okay, now we take the matrix. Okay, take the matrix of F2. That's what I've done by putting brackets around it. Well, again, this is just a representation, so I just put, since it's a valid representation, I can just multiply the matrix of E1 times the matrix of F1 times I. And what we get is a matrix of F2 is equal to 1 over the square root of 2 I times minus I. Well, if you look at this, I times, that's like the Pauli matrix for 1 minus 1. Remember, the Pauli matrix for E3 in the geometric algebra G3 is 1 minus 1. I'm just multiplying that matrix by I, and I get I minus I here. And that's now the matrix of F2. Well, if you check that, square this thing, you'll find that we get 1/2, and then we have minus the identity matrix. Okay, I squared is equal to -1, minus I squared is equal to -1. So you see that the matrix of F2 squares to the minus the identity matrix. Well, the only other interesting thing is calculating, excuse me, calculating the matrix of A3, okay? So calculating the matrix of A3, well, you just take the matrix of E1 and add it to the matrix of F2 divided by the square root of 2, and you get this matrix. I've never seen this matrix before, but I think it is interesting. If you square that matrix, you find that that matrix square is an idempotent. Well, it's a nilpotent, okay? So if you square that matrix, it's very easy to calculate that this matrix squared is equal to 0. Well, that's what we said. We said that A3 had to be a nilpotent. Now, if you also calculate the symmetric product of these matrices, you'll find that they're all equal to 1/4, which is exactly what we wanted. So we wanted three null vectors, A1, A2, and A3, whose inner product is 1/4. Well, you can see we can translate all that into matrix statements. So for example, A1 times the matrix of A1 times the matrix of A2 plus the matrix of A2 times the matrix of A1 is equal to 1/4 times the identity matrix. Well, you have to check that. Well, that's equal to 1. Actually, that's 2. If you check it out, it works perfectly. There's no problem with that. Okay. Okay, now the interesting thing is I'd like to go to the next highest symplectic algebra generated by 4 null vectors which have square 0. So that's what I'm denoting by S4 plus A1, A2, A3, and A4. In this case, we define row 4 equal to 1/2 to the 3, which is of course 1/8 in this case. So we want these nilpotents, null vectors, to satisfy AI dot AJ is equal to 1/8 delta IJ times. Okay, what did I do here? Okay, I don't know what, there shouldn't be a J there. That J should, so it's just 1/8 delta IJ. I got an extra J in there. Forget this J here.
Yeah.
Okay, so we want to use the same A1, A2, and A3 that we used for G3, okay? So basically we want to use the same A's, but there's a problem. Okay, we like to go from A3, basically modifying the definitions of these null vectors, A1, A2, and A3, and A4, so they satisfy the new rule. But in the process, we have to go from 2x2 matrices to 4x4 matrices. And actually, there is a problem here. For my ideas, I haven't solved the problem yet, which is why I'm trying to clarify exactly what that problem is here. Okay, so in terms of the standard bases, E1, F1, and F2, that's the standard basis for G1, 2. Well, the A's were defined by E1 plus F1, E1 minus F1, and E1 plus F2, okay? And if you calculate this outer product, you'll find that's just equal to 2 F1 times E1 times F2. Well, we can write it more standardly by anti-commuting E1 and F1. You get minus 2 times E1 F1 times F2. So that's the trivector of the geometric algebra G1, 2 here. And these are basically A1, A2, and A3 here. But notice here now, we use E1 for defining the null vector A1, E1 defining the null vector A2, and for E3, we have E1 plus F2, so that they all use E1 here, E1 and E1. And of course, that's what we need in order to keep these inner products equal to 1/8. Well, in the two-dimensional case, well, that's the three-dimensional, A1, A2, and A3, we want 1/8 times delta ij here. And that works fine. But now what we want to do is we want to extend this geometric algebra G12 to the geometric algebra G22. So we have to add a new Euclidean vector E2 to the mix. Okay, so we have E1, E2, F1, F2. These are all anti-commutative. E1 squared equal to E2 squared equal to 1, F1 squared equal to F2 squared. Well, that's just the same as before. So that's the neutral basis of the geometric algebra, sometimes called the mother algebra by other people's terminology. But we know how to represent that geometric algebra in terms of 4x4 matrices. But the question is, can I represent them in terms of these four null vectors, A1, A2, A3, and A4? Well, we can think about A1, A2, and A3 as being defining the light cone, okay, in three-dimensional space, Minkowski space-time.
Jesus, are you still there?
If there's a problem with the
Yes.
connection. Yes.
Yes.
We lost him.
He's disconnected. I expect he'll come back.
Yes. Mhm.
I guess my only comment so far is that I'm sort of looking, sort of
Okay.
thinking about applications.
Yeah, I had a,
Yes.
can you hear me now again?
Yes, yes, yes. Yes, we can.
My hotspot is not the best. Okay, so can you see the slide again?
No,
No.
it's not at the moment.
Okay, so I guess I have to, maybe I have to share my screen again or something here.
I think so. Yes, that's good.
Okay, can you see it now?
Yes, yes.
Okay, good. Okay, so again, we are noting the fact that E1, E1, and E1 are used to define the geometric algebra G12. But now we have when I allow E2, that defines the nilpotent again, E2 plus F1, that's a nilpotent because these are anti-commutative. You square that, you'll get well, a proposed candidate for A4, but the problem is here is that notice that E1 times F2 is completely orthogonal to E2 and F1. So these two vectors will anti-commute, which says their inner product will be equal to 0. Well, I don't want the inner product equal to 0. I want it to equal to 1/8. Well, these ones, I can adjust these by simply taking A1 prime equal to 1 over the square root of 2A1, A2 is equal to A2, 1 over the square root of 2A3. So I'm just adjusting the scale factors for, this was A1, this was A2, and this was A3. But I cannot define my A4 equal to E2 plus F1 because it doesn't satisfy my requirement that the inner product of these things will all be equal to 1/8. No, the question is, can I redefine, maybe using E1 plus E2 plus some combination of F? I want to get 4 nilpotents, 4 null vectors, which when you wedge them all together, you get the pseudoscalar of the algebra E12, F12, and which will also give us the 4x4 real matrix representation. Now, the question is, can I define these null vectors in the way, or is that just my imagination? For some reason, I believed I could do that, but now when I'm actually filling in all the details, I do have a problem. So can you understand what the problem is? The problem is I can define this part of the with 2x2 complex matrices, but in order to use a 4th vector, I've got to go to 4x4 real matrices. But I hope you can see that this is an interesting problem, because, well, we're talking about matrices. I consider a matrix to be the coordinates of a particular geometric algebra. The geometric algebra really is what contains the geometry, whereas the matrix is just the coordinate matrices of a geometric number. Well, of course, there's more than one way of interpreting these coordinate matrices, but a matrix plays a subservient role to the geometric algebra, which is really where the geometry lies. And of course, all the different geometric interpretations give you space-time, they give you the Dirac algebra, they give you everything. But with the geometric interpretation, the matrices by themselves hide the geometric interpretation. Okay, so I guess I can go to the other.
Your problem then is looking for this null vector basis, this A1, 2, 3, and 4.
Yeah, I'd like to redefine A1, A2, A3, and A4 such that the inner products are all equal to 1/8. Well, I could simply define this, that adjusts the scale factors using the old definition, but that's not good enough because I've got A4 to define. Now, it might be that in 4-dimensional space, it's not possible. I don't know really, but again, we're in the geometric algebra G22. Maybe it is possible. For some reason, I believed that it was possible. I thought I could do it, but when I look at the details, I have a problem, so, which I'm sharing with you today. But I think it is very interesting.
The problem that you're presenting is not necessarily the question of whether or not it's possible, but rather you're looking for an extension of the algorithm in effect.
Exactly.
So you used a particular, what seemed to be a general algorithm going from 1, 1 to 1, 2, but going to 2, 2, that same algorithm doesn't seem to give you the basis that you're looking for.
Well, we can go from 2, 2 to 2, 3 just by complexifying the 2x2 algebra. But now we have to go back to a real algebra. It's very interesting. I find it a very interesting problem. Maybe I can do it. Maybe, for example, we can write E1 plus E2, or 2E1 plus 3E2, and we still have F1 and F2 at our disposals.
What if you avoid the complexification at the beginning? In which case you would have to go to the 4x4 representation.
Okay, that's right.
Just to get 1, 2, right?
That's right. That would be, yeah, obviously we can do that. So that's the next step actually to do that. I just wrote these 2 pages yesterday. So that is a good way of proceeding. We can do that.
I think it's perhaps simpler to avoid complexification and always use real matrix representation.
I think that's a good idea.
In which
That's
case
right.
the algorithm for going from one to the other may be more transparent.
Yeah,
Um,
yeah, that's right. So the three-dimensional going, the fact that it exists for 3x3, 2x2 complex matrices, well, we know that that implies that it exists as a real 4x4 matrix. We can just,
Mhm.
we have a representation of E1, E1, yeah, E1, E2, F1, and F2 as a 4x4 matrix. And now it's just a matter of that's right. So that's a good way of proceeding.
For
But of course,
example,
then you have to remember, well, I guess you can simply use the Dirac matrices. Well, then again, for the Dirac matrices, you're representing the Dirac algebra, which is of course based on E1, E2, and the even subalgebra of the Dirac algebra is G3. So again, well, I do give these representations in this.
Yeah, in an earlier
book.
paper, in this series of papers, you showed a generalization of the Dirac algebra.
Yeah, in this book here, I also have it other places. There is a representation of the real vectors, but again, you have to write them down. I don't have access to Mathematica here, and then you're stuck dealing with 4x4 matrices. So, but the real matrices, I think that is the proper way to proceed. Yeah, on page 85 of this book. Well, there you have it. Let's see if I can. I'm just looking at page 85 of. I think I gave you all a copy of this book, so you can
Yes, I
get
have
the
a
representation out of there. It's easy to find it. So
because we either can go from Pauli matrix, for example, to quaternions, no? And then we go from one two-dimension matrix 2x2 to 4x4, no?
yeah, we can easily go to from G11 to G22 by going from real 2x2 matrices to real 4x4 matrices. But we don't really have to use the Dirac algebra. We should really just use the real algebra, E1, E2, F1, and F2. But that's the thing. Yeah, so we want to stay in the neutral geometric algebra, G22, because that's a real algebra. We can very easily get from G12 to G3 by simple identifying a re-identification of the vectors E1, E2 as bivectors. I've done that several times, and we have, it's very clear how to get, there's an isomorphism between G12 and G3. You just multiply I times to change the signature of the two null vectors F1 and F2 by multiplying by I, okay? And then you have the representation of G3 by just reinterpreting the two pseudo vectors F1 and F2, replace them by I F1 and I F2, and they become bivectors, which of course the Dirac algebra doesn't show that at all, that there's really a geometric thing that's taking place. You're replacing pseudo vectors by bivectors, which have squared plus 1, which physically must mean something, or you going from G12 to G3, that's almost like going from, it's very interesting what it implies physically. And that's why I think that these ideas will be useful in understanding better the geometry behind quantum mechanics.
Yes, and I found a paper that present a work similar to your ideas of going from, in this case, from Dirac algebra to one geometrical representation of this. I have here in my papers, maybe I can show to you the principal ideas that I found in this, but he works with first with Dirac algebra, and after relate with Clifford algebra in this graphical representation. Then it is interesting because he relates two nodes in the graph by two different gamma matrix, and then the transformation from one, the product of one matrix with another matrix is related like the edges of the graphics. Then I think it is interesting because it's similar to some ideas that you have presented to us.
Well, could you send me a copy of that paper? If you could send it to me, I'd like to take a look at it, of course. That's the thing. That's the whole idea, is to be able to apply this to graph theory by naming the vertices of a graph with these null vectors. It seems to be, that's my main idea, which is why I use the term light cone projective graph geometry. But again, I do posit that on the existence. I believe they do exist, but I haven't been able to. I should be able to find them in terms of these F1, E1, E2, F1, and F2. Probably there's a simple. It's like a decomposition of a number into, like, 6 is equal to 2 plus 4 plus 1 plus 5 plus, and it looks like the same type of thing. It's just a decomposition type idea of represent. There are many ways, of course, people do that for in number theory or in many other areas of mathematics, or idempotence and so on, that sum to unity. So anyway, this is where I'm at right now. So we can go to the, if you like, I can go to the other paper, or maybe you have something more you want to say about it.
Well, I just wanted to step back a minute and sort of understand your motivation, right? Because you started out with the sort of the general idea that one could conceive of the null vectors as a representation of Clifford algebras, right? So that,
exactly. Yeah, that's the whole thing. I'd like to. This is quite different than this with using the idempotent. Okay.
But you were emphasizing, I think, also that historically there was a move to going to matrices, matrix representations, at the same time as Clifford and Grassmann were discussing, and Cayley, I guess, as well. They were discussing whether or not matrices really needed, right? In what sense they were needed, or and that I thought it was intriguing that you were effectively suggesting that we could avoid the concept of matrix altogether,
Exactly. Yeah,
in the sense that we don't really need matrices, but we do need representations of Clifford algebras, and one way of getting those representations would be through these through compatible Grassmann algebras. So
exactly.
yeah, so that seemed kind of interesting, and a little bit more abstract than what you're doing here with the question of matrix representations, right? Which are
Yeah, I actually think all of linear algebra could be done in terms of these null vectors. And of course, that's what I'm trying to do.
yes. So I think that's sort of the core of your thesis here. Right?
Yeah, I would even say that there's an oversight of the 19th century mathematicians. I mean, you know, Cayley, they call it the Cayley-Hamilton theorem. That why it got the name of Hamilton was because Hamilton proved the Cayley-Hamilton theorem in 3 dimensions using quaternions. Okay, but actually it was only with Frobenius toward the 20th century that they actually proved it using matrices, and then they forgot about Clifford algebra altogether, or Grassmann algebra. So I think that they of course generalized it in many different directions with Cartan, differential forms, and all this, but they really missed the basic ideas of Grassmann to begin with, which is why I've been. It's too bad that Clifford died so young. He probably would have changed things the way we were thinking about things today. Instead, they went off in all different directions, and we have today's mixture of, well, then we have category theory added to the mix as well.
Because it looks like the problem is the kind of product that we are using here. Because if we use a tensor product, then we can go perfectly from matrix 2 by 2 to matrix 4 by 4 by tensor product. And is the way that in this paper are using the author. Then I think that if in the definition of your product, because you are defining if F and E by in terms of A, in terms of A, and then after you define new elements in the product of E and F. And then if we use here tensor product, maybe we can get a more different kinds of elements that can made possible the construction.
Yes. So are you suggesting that instead of a matrix representation, we would have effectively a tensor representation?
Yes, I think that it is.
Well, but basically, I believe that geometric algebra is even more basic. You can represent all of tensor algebra in terms of geometric algebra.
But you have to be clear what you mean by tensor in this case, right? You mean something like Cartesian tensor or
yes,
something like this, right? So you don't mean tensor in the physics sense of the word, right? But rather in
I actually prefer this approach that Bill has suggested. We just go to the 4 by 4 matrix representation, and we try to we'll keep it real and try to define, well, I like to define these,
But
light cone.
but I think these are related in a sense that and it's what as you just said, it perhaps is involved in the definition of the multiplication in the representation. So if you could go, for example, to what you would probably refer to as a Kronecker product between
Yeah.
two, right? So the Kronecker product would give you still matrices, but they would have a kind of structure due. So you'd be going, say, from a 2x2 matrix with a Kronecker product to a 4x4 matrix.
But of course, people do that already. They do
Yes.
extend matrix multiplication to higher dimensions using the, but I think the most basic idea is that's right. You have to define the vector E1 as a 2x2 real matrix or by 4x4 real matrix or 8x8 and so on. But actually more fundamentally, it's just anti-commutative properties that really we're talking about to define these vectors. Orthogonal vectors anti-commute in any number of dimensions. And for graph theory, of course, the outer product, which is a determinant, determines the areas of the faces. And of course, we in graph geometry, we can do all these inner products in terms of the faces of the simplex that is defined by these vectors. And rather than using the Euclidean signature in graph theory, you're using really the areas and hyper areas of higher dimensional objects but let's see, how would you represent? Yeah, well, so a line segment can be represented in terms of an outer product of 2 points. And of course, then we're not using the Euclidean distance, but rather representing it as an outer product. And so in a certain sense, area, line, bivector area, volume elements, and so on, also define a metric, which is in a sense equivalent. Well, projective geometry, as Kaylee said, projective geometry is all of geometry because there's various ways of interpreting an inner product. Anyway.
Yeah.
Well, it's my personal philosophy would be to avoid matrices, right?
Exactly. I don't like matrices. Well, they're, like I say, they're coordinate matrices, nothing more than coordinates of a vector, that's all. But instead of using just the usual vector space as a column vector, well, I don't like that idea. I think that's covering up a lot of, or for example, a dual vector. I don't emphasize dual in terms of a functional, a mapping from vectors to scalars. Anyway, there's some philosophical differences that the way mathematics is developed is kind of restricted our way of thinking about things, I think.
Well, originally, it's interesting that originally our discussion did start with the notion of duality and the relationship between a row vector and a column vector is the kind of duality that we started to talk about at the beginning, like the relationship between a vector and a covector, right? But this kind of structure, the structure that you're talking about now with like compatible null vectors, is not clear to me how that relates to the first kind of duality.
Okay, can I go to let's go to my other screen, my other revised paper, and I want to show you one thing in that paper. So I'm going to cut this out here, and I'm going to go to another share screen here. let's see, I want to open up this other paper here. Okay, now I need to share screen again here. I don't see it. Let's see here. Can you see this new paper again?
Yes, we can.
Okay, so it says light cone projected graph geometry. You can see that?
Yep.
Or not?
Yes, looks good.
Okay, so let me go down to this paper and I want to show you something that I think is very interesting here. Okay, so that's in three-dimensional space. You can see these are light. This is a light cone in dimension 1, 2. Okay, so that's we have A1, A2, and A3 are just the angle between these two vectors are exactly what we have. Okay, so that's one figure. I don't have many figures developed here, but let me just go down here. Okay. Okay, so we're looking at the geometric algebra G11. The way we represent the position vector in G11 is just x1, x2. Okay. Now, the interesting thing about that representation is, okay, I want to look at this. So here's a linear transformation. Notice that the vector is not a column vector anymore. It's a 2 by 2 matrix, 0, 0, x1 and x2. And of course, this is determinant v1, 2, v2, 1, and so on the diagonal of this thing here. So the representation, we can use 2 by 2 matrices throughout. We're not stuck using a column vector in the final place. So it's a completely different idea. And of course, in n-dimensional space, while we're talking about, well, we're representing a graph. Actually, this is the area of a face of a simplex here, these V1 and V2 here. But the interesting thing is a function, the position vector is now represented as a 2 by 2 matrix or an n by n matrix. Okay, so that's really what I wanted to show you, replacing column vectors. When you represent points by null vectors, then we have the possibility, instead of representing everything in terms of column vectors, we can represent everything in terms of n by n matrices. That's really the point I wanted to make. Well, okay,
So-
here I'm going to the sign stuff.
Can I ask a question about that? There, where you have this, the last matrix, so in the off diagonals, you have x1, x2, right? So if you generalize that, say, to higher dimensions, are you always going to have like only the off diagonal? So in a 3 by 3 matrix, you're going to have like x1, x2, x3 along the anti-diagonal? Is that what you're?
Well, of course, what I've done can be extended to the complex case for A1, A2, and A3 without any problem. We just complexify x1 and x2, and so these become complex numbers, which are represented in terms of the pseudoscalar element of F12 of G12. Okay. Now, if we go to higher dimensions, I can't. Yeah, I don't know. I haven't really. This is where I'm at, really. But I'm trying to understand by looking at these sequences here. I'm trying to understand better what's going on here. Yeah, it's difficult to explain exactly what's taking place here. But again, this last section, I think, makes more sense. FSN plus, well, again, you can see, but that's the thing. I am assuming that we have these n null vectors, A1 up to AN, which satisfy, well, okay, so I'm trying to extend from what I mean by the notation G001. All I start with is one null vector. So we start with one null vector. We extend the real number system by one null vector, which is a vector which has square 0, but is not equal to 0. So usually we define geometric algebra by inventing, well, first of all, people extended by a complex number, I squared equal to -1. But that's not sufficient to get geometric algebra. You need to extend also the real number system to include vectors which have square +1. Okay, so we have G10, for example, that's PQ, but here what I'm emphasizing is the idea you extend the real number system to include a new quantity which is not 0, but which has square 0. That's a nilpotent. And in fact, if you extend by n nilpotents, which are anti-commutative, then you get exactly Grossman algebra. So I would identify the Grossman algebra G00n as just the n-dimensional Grossman algebra. They're anti-commutative and they have square 0. So the Grossman algebra, you can think about it as extending the real number system to include n anti-commuting null vectors, and that's all. Okay, but now going to GPQ, well, then we see that null vectors are actually defined in terms of, well, if you take E1 plus F1, E1 and F1 are anti-commutative, then you get E1 plus F1 is a null vector. So it's then you talk about all kinds of isomorphisms if you want to. Okay, so now I'm defining, we take Rn, take V1 up to Vm in Rn. And I assume that V1 up to Vm is not 0. And I define A1 up to An by this notation. And I have just notation I'm using to represent these ideas. We leave out the ith vector and we get a face of the, so if we think about A1 up to An as the end points of a simplex, then we leave off one vector, we get a face of that simplex, okay? So for n equal to 3, for example, if I take this, these are the faces of the simplex, A2, 3, leave off the one vertex, V, which represented by A1, and then we have A1, A3, these are just the faces of the simplex then. Okay, the set of vectors Vm are linearly independent. Okay, that's just notation I'm using. So I'm thinking about Vm plus defining m minus 1, which is m minus 1 faces. Each m minus 1 face is geometrically represented by the n minus 1 vector, which we leave out. Okay, so these are the faces of the M simplex then. Well, okay, here I'm trying to relate this to projective geometry by the simple null cone. But again, this is very just intuitive ideas. So these are the null cone in two-dimensional space, A1 and A2. Okay, and of course, in this case, these are perpendicular vectors defining the null cone in G11. Okay, and then these circles are just, this is a unit circle, then a half, a fourth. So these are relating the numbers row n. Okay, so row 1 is the unit circle, and so on. and they cross, just trying to give some idea of where projective geometry is becoming involved. We can think about projecting these circles onto the line at y equal to 1 in R2. Well, that's the main idea. Well, I'm trying to relate it to platonic solids, but maybe I shouldn't have even published these this preprint, because they're just, the ideas are pretty rough. And now I find I have to be able to, I have to go back and just define these. I hope that these null vectors A1 up to AN, which the inner product is equal to 1 over, well, equal to rho n. I believe that that's still true, but I can't say. I think I'll follow up on Bill's ideas and trying to represent it in terms of, we can represent it easily in terms of real n by n real matrices. Well, it would be 2 to the 2n, but of course these matrices grow big, so I'll be happy if I can get it to G22. I think it'll be clear once we can, if I can find it for G, going from, well, we'll see how that works out, but that's where I'm at right now. But this is interesting how this would work out then, because I've actually calculated these things. For example, if I take x squared, so, okay, so I represent a point x then as just position vector xi ai, and it's a position vector in Rn. Well, as a subalgebra of Rn, okay, so actually I could just let m equal to n and stay in Rn, but I'm trying to think more in terms of general graphs. For a general graph, the outer product, there will be a limit. The order of the graph will determine what's the largest linearly independent faces that you can have. Where if the graph exists in m-dimensional space, then there's only, you can represent all the points then in terms of supposedly the linearly independent null vectors. Anyway, so I assume that A1 up to AM is equal to, not equal to 0. And then I calculate, notice that if we're in the first quadrant and we're using barycentric coordinates, then all the coordinates will be positive. Well, that's very convenient because then I can define the magnitude is rho n times the magnitude of the faces then. Well, the two faces, xi times xj, and that's larger than 0, and I can define a unit vector. So I'm trying to develop the idea of analysis. And okay, now I can try to define the gradient in this LPGG calculus in a natural way. I have rho n, again, is 1 over 2 to the n minus 1. And I just define the gradient as I leave out these faces times the partial derivative with respect to I. Okay, well, now we look at the three-dimensional case. The gradient would be A2 plus A3, partial x1, A1 plus A3, partial x2, and so on like that. And now if I calculate this, then I have shown that it gives you exactly rho n times n minus 1 over 2, which gives you the number of faces of this, two faces of this. Well, we're talking about a simplex S3, so that's the tetrahedron. No, S3 is just the what is it called? It's the what's the tetrahedron?
Yes,
three-dimensional space.
Tetrahedron, no?
Yeah, it's yeah, that's just Yeah, with 3 points, that's just a triangle. That's right. So it's just a triangle with 3 two-dimensional faces then. Okay, so 3
Okay.
times. It's just 3 faces of a triangle. That's right. We're just looking at a triangle. That's all.
Have 3 vertices.
An equilateral triangle. Okay. So a tetrahedron is the next interesting case. Of course, that's where we have to go to. So there's no question about 3 by 3. We can use 2 by 2 matrices to represent S3 as we saw. But of course, we do want to represent it in terms of real matrices. So that would be real 4 by 4 matrices then that we're using then. But with S3, there's no problem. And I can actually show that these formulas are correct. The gradient operator squared, or the Laplacian, is just equal to this quantity here. And if you take these signs here, if you take that, you get row 3. That's in this case, it's 1/2 to the 1/4 times gamma 1, well, partial derivative squared, x1 partial derivative squared, x2. That's the usual Laplacian plus these mixed partial derivatives here. And if you calculate the Laplacian squared of x squared, you get this formula. These formulas certainly work for n equal to 3. Okay, no problem. I've worked out the details there. But again, well, now I have this conjecture. Very interesting. Maybe it's not true. At first, I was convinced that it was true. Now I'm not so sure because well, you can see where I'm at really. I shouldn't have published any of this stuff, kept it as preprints, but well, because I was traveling, I wanted to get something down before I traveled. Anyway, you might look at very interesting n-platonic solids. The number of n-platonic solids is given by 1, 1, infinity, 5, 6, and then 3, 3, 3, 3. Well, the first thing I would like to do in graph theory is really study exactly how these ideas are related and hopefully either disprove or prove this conjecture, one or the other. So anyway, you can see where I'm at. I think Bill's suggestion of looking at R22 is the next thing to try to find these A1, A2, A3, A4, which all these ideas depend on. I think it's true, but we're talking about a light cone in 4-dimensional space. Well, that we're not really talking about the Dirac algebra. We're talking about the algebra G22. So the light cone might well allow but if that's true, then like Dr. Cruz mentioned, we can do away with matrices altogether. Well, in fact, we know we can do. We don't need matrices. We can do all linear algebra in terms of geometric algebra. But matrices are convenient. They've been well studied, implemented using computers, rapid computation. So, like I say, a matrix is just the coordinates of a geometric number. There's many different interpretations, but still, a matrix is just the components of a geometric number in any number of different geometric algebras. So.
It occurs to me that that if Dr. Leszewicz were here, he might accuse you perhaps of reinventing Grassmann algebra. Right? It's like he would say, from your point of view, you're a Clifford algebraist, and you're just now rediscovering what you said.
Okay, but I would say that
the history
I would say that criticism applies to
Grassmann,
Cayley and Frobenius and those guys in the 19th in the 19th century as well.
Yes, but it's like a archaeologist rediscovering this, but from the point of view of now Clifford algebra as being the focus, right? But what Oshevich published a paper quite a long time ago in the 1970s, I think even, was a paper that said, well, and I think it started actually when he was, as a young professor, he was introduced to Hestenes, right? And there was a long period of time when the Polish, this is what my history, my distorted history, and you perhaps, Dr. Sobczyk, you're much better aware of how this developed, but it was
No, not
as
really,
if,
not really.
Dr. Hestenes presented a lot of his earlier ideas in Poland, right? And Oshevich was one of the people who was involved in those seminars, and it was Clifford algebra, and the idea of a geometric algebra at the time was a sort of a interesting, new, challenging idea, but it seemed odd, I think, because at least a lot of the earlier sort of training in linear algebra, at least in Poland or in Europe in general, involved the notions of Grassmann, and that it was so it was very natural to think that Grassmann algebra was fundamental. Clifford algebra was just a kind of an add-on or an addition, that it didn't, in a sense, it wasn't necessary, right? So that,
Well, of course, you can
and
say that
that was
about,
the point.
you can say
The
that
point of
about
the paper I'm
quaternions
thinking
as
of.
well, of course.
Well,
Quaternions,
yes, and yes, that's right. The point was that if you started with this Grassmann algebra structure, the Grassmann algebras had a natural sort of built-in dual. So when you get one Grassmann algebra, you naturally get a second Grassmann algebra, and they have this relationship that gives rise essentially to all of tensor calculus in the end, right? But it's all expressed in terms of the Grassmann algebra, of the two Grassmann algebras, right? And the relationship between them. And then this paper I'm thinking of said, well, the same thing applies to Clifford algebra, that in order to get Clifford algebra from Grassmann algebra, we need these two Grassmann algebras, and we need to define what we mean by a metric, which is to say, we need to define something that defines an inner product or a scalar product, right? And that additional structure that you add on to the Grassmann algebra is all you need in order to do geometry from the point that otherwise would require Clifford algebra. So that's why I'm in a sense saying, well, in a sense, you're sort of rediscovering this by saying that Clifford algebra has a representation in terms of compatible Grassmann algebras.
no, that's the thing. I'm not really sure exactly how Grossman actually published some late papers on relationship between Grossman algebra and Clifford algebra, but I think there's more than one way of getting that relationship. As far as I know, this idea of two compatible Grassman algebras, I don't know whether that's the way Grossman did it. Now, people have invented the regressive product and all this type of thing on Grossman algebras as another way of looking at getting, well, differential forms. They have a regressive product and all this stuff. So it seems like, yeah, okay, but that's not really compatible Grossman algebras. They're putting scalar products on Grossman algebras, inner products on Grossman algebra. So I'm not quite sure exactly how Grossman himself looked at it. Well, maybe whether Hestenes clarified these ideas or not, I'm not sure about that either. Maybe I need to take a look at exactly what he wrote about that. I'm not sure.
But can you define what you mean by compatible Grassmann algebras without involving the metric or without involving a scalar product?
Well, that's the thing now. I start by considering the real numbers. You can extend by null vectors. So I start by assuming that all the rules that we're going to assume are exactly the rules of usual matrix algebra. I don't want to define a field. I don't want to do any of that. I know people understand the rules of matrix algebra, so I'm assuming that what I call the algebra N, I denote it by an N, consists of null vectors and their products using the usual rules of matrix algebra. Okay, that's all I assume. And now, okay, you can see that N will contain all the Grassmann algebras because, well, all null vectors which are anti-commutative define the Grassmann algebras. But now when you talk about compatible Grassmann algebras, I'm not sure, did Grassmann talk about two compatible Grassmann algebras as I'm talking about them? I don't know about that. It seems like a natural idea. Well, that's why I started. AB plus BA is equal to 1. Okay, are we really putting a metric in there? Because A squared is equal to 0 and B squared is equal to 0. When I'm saying that AB plus BA is equal to 1, is that we're putting an inner product on null vectors? Does that count as a inner product? A null vector has square 0.
You're saying it's perhaps something a little more general. I'm not sure. No, I don't know.
Well, that's
But
right.
it
So I
seems
think
related.
that we're expanding. I think it's well, people have studied the real numbers extended by one square 0. So that, I think that's an important idea, just as extending. I don't know why people still are not thinking about real numbers extended by, okay, everyone likes the complex numbers. Okay, I squared is equal to -1, fine. But there's a little more problem with extending the real numbers with new square roots of +1, okay? So I define a unit vector, a Euclidean unit vector having square +1. Okay, of course, that makes the real numbers system extended to include E1 squared equal to +1. It is not a field anymore. Okay, so it's not a field, big deal. Well, people, of course, originally didn't want to accept complex numbers because how can you have a number which has square -1? A real number only squares to +1. So again, it's just an extension of the concept of number that we're talking about. And it's stopped mathematics for centuries, actually. As you know, Greek, Egyptians didn't want to accept, they only wanted to accept unit fractions, 1/3, 1/2, 1/5. And they wanted to express everything in terms of sums of unit fractions. Well, okay. But, well, of course, in our century, the 20th century, 21st century now, we want to extend to higher dimensional spaces for Minkowski space, time, whatever. So what we're really doing with geometric algebra, we're setting down a new set of algebraic rules, which allows us to understand higher dimensions. Well, of course, that's exactly what Descartes did with the Cartesian geometry, Rn, for example. But with geometric algebra, we're also extending rules, orthogonal vectors anti-commute, and that's about it. We're just one more simple rule, which allows us to picture higher dimensional spaces, in addition, giving more geometric structure than just Rn. It's just coordinate vectors, and so on.
But isn't what you're doing really just reinventing Grassmann algebra, right? Like, in the sense that you start with real numbers, and then you start you add something new, something, maybe you're going to call it a vector, or you just call it something new, unknown, that is not in itself a real number, but whose square is 0. Right? So as soon as you start doing that, you're extending the algebra of real numbers into a new algebra. But is that new algebra more general than Grassmann algebra?
No, I don't think it is. In fact, Grassmann himself believed that Grassmann algebra was fundamental to mathematics. And why was his ideas ignored for centuries? And then they're just taken off with differential forms, Cartan, and any number of other ways. Well, then you have duality as functionals, and mathematics has just exploded in ideas. Well, yeah, maybe nothing's new. Everything is old. It's just that we're rediscovering.
Well, the new part, perhaps, or maybe it's not completely new, but the new emphasis would be to focus on how Grassmann algebra arises as a kind of geometry based on the notion that you have new things besides new kinds of numbers besides 0, whose square is 0, right? I mean, just by extending the real numbers, you end up maybe with at least a generalization of real numbers that is geometric or pre-geometric. At least it doesn't yet have any notion of distance or of length, or it doesn't have an inner product or a scalar product, but it has some of the properties of geometry. So it has properties like orientation, and so by just extending the real numbers with null vectors, in effect, or
Okay,
giving them a Grassmann structure, then you've gone part way towards geometry.
Okay, I think graph theory, there are people that use Grassmann algebra in graph theory. I'm not sure exactly how they're doing it, but that's exactly, of course, what I'm trying to do. I want to name vectors in a graph, or vertices in a graph with null vectors. Well, I guess we can always do that, but then, yeah, well, there's no problem with naming points in a graph, but then I want to get the geometric algebra structure in there as well. So that's when I introduce, well, yeah, I don't know what people use Grassmann algebras in many different ways, and they use matrices for example, in graph theory as well, adjacent matrices and all kinds of stuff. Of course, immediately you use adjacent matrices, and of course, a matrix is just the name of a geometric number in a representation of a So all these ideas are really the same, really, in one sense or another. The question is, what is the best way of thinking about things, or the way that helps our intuition? I think the idea of orthogonal vectors anti-commute in a Euclidean space, in an anti-Euclidean space, or pseudo-Euclidean space, is a very important geometric idea that needs to be emphasized in talking about geometry in higher dimensions. Of course, physics now demands relativity theory, and string theory, of course, is in 10-dimensional space. Well, that's the idea of these Platonic solids. For example, how many Platonic solids are there in 6 dimensions or 4 dimensions? In 3 dimensions, there are 5. In 4 dimensions, there are 6. But after that, there's only 3 in all higher dimensional. How do you understand those ideas? Well, people understand those ideas, and that's why very interesting papers, which I've referred to in these references here, 2, 8, 9, 10, and 17. Very nice material that's on the web about those ideas. But anyway,
well, just to mention one other connection, and that is with Frobenius algebras, and that is the notion, for example, that you can make Grassmann algebra Frobenius in many different ways. That was actually, I think, Oshevich and I actually did some initial little collaboration about that, just to show that that's the case. And by making something Frobenius, it means giving a mapping from the vectors or the elements of the Grassmann algebra into the real numbers. So you just have a way to take any element of the algebra and map it into a real number as a kind of measure in a way. Right? So it's prior to the notion of a scalar product. Is usually referred to as the Frobenius form, right? So that you just take some algebra and you add a Frobenius form in order to get a Frobenius structure of that algebra. And that from the Frobenius form, you can get a scalar product because you can show that this scalar product is always the usual algebraic product of two elements followed by by applying the Frobenius form to it. So this for a while, Oshevich and I explored this for small number of dimensions, algebra of small number of dimensions, to show which, like, what are the constraints on the Frobenius form that give it a Frobenius structure, give any algebra a Frobenius structure, and that was sort of it doesn't involve necessarily any notion of metric in the usual sense. Like from the algebraic point of view, all you're doing is introducing a new operation that maps the elements of the algebra into real numbers.
Well, but of course, isn't that what I'm doing when I say compatible Grassmann algebras? It's not really a metric either. But then, of course, I talk about the geometric algebra G22 or G23. It can be interpreted as a metric structure, but it doesn't have to be. And in fact, each observer has his own subalgebra of the Dirac algebra. So I don't think that it should be so cut and dry. I don't like this idea of a quadratic form being such a hard structure. Every observer has his own quadratic form. Well, okay, that's fine. And you have all these theorems in linear algebra about it, but it's too cut and dried. I think the idea of an observer in a reference frame depends upon velocity and so on and so on. It's too rigid structure that I think people have built up around the notion of a quadratic form.
But I'm not like, if you go down that direction, then this connection with Platonic solids and so forth seems less obvious, right? Less even less geometric. I'm just wondering if it isn't kind of a distraction from at least from your original main theme, right? That there's and even the connection with graph theory seems a bit remote to me. Like it's not. It's not clear to me what you would like to get from graph theory, that in a sense that you don't sort of already have.
Okay, well, like I say, the idea is simple. I like to name. Okay, I'll take care of that call later. Yeah. Yeah, so, yeah, well, of course, when they talk about Platonic solids, they're only talking about Platonic solids in the Euclidean space of higher dimensional spaces. They don't talk about, I never heard of Platonic solids in hyperbolic geometry. If there is such a notion, I'm not sure, I don't know. So, but But that's the thing. So geometric algebra, GNN, that's the thing. Matrix algebra can be defined in terms of geometric algebra of neutral signature, GNN, or as a complex. I think the two basic geometric algebras are GNN and GNN plus one. And that's what I've been concentrating on here, actually. The earlier versions were a little more my ideas were a little bit less clear, but those are the geometric algebra. Well, first of all, again, whenever you talk about adjacent matrices, you really have geometric algebras immediately involved if you want to look at it in terms of geometric algebra, because every matrix algebra is a coordinate matrix of various different geometric algebras. So you automatically have geometric algebras involved, whether you want to talk about them or not, when you talk about matrix algebras. So graph theory is, matrices are well, there is a paper by an MIT mathematician, a Russian, about Tanya, I forget her name, but you can look it up in the reference I gave in the revised version. She uses Clifford. She was very excited about these ideas as well, as she relates in her paper. You might want to look at that paper. It's one of the, I can go to the bottom here. Let's see if I can look at the references here. Yeah, okay, so Baez, I look at I think it's a beautiful, what he's done with with Platonic solids. You can find at HTTPS. I would strongly recommend looking at that. It's beautiful what he's done with the handling his graphics is just fantastic. I'll never have that possibility of. Okay, so look at this paper by Tanya Kovanova, Clifford Algebras and Graphs. You can find the paper at HTTP, ArchiveX, and so on. Very interesting application of Clifford algebras to graphs. And of course, I think I'm trying to relate Clifford algebras to graphs in a much more direct way by insisting that vertices of a graph be named by null vectors. But she does this in a much more general way. So I need to study that paper myself to understand exactly how what I'm trying to do is related to what she has done in her paper. But she was extremely excited about this paper as she relates in her acknowledgements.
But here the purpose of your ideas are different, no? Because we are trying to get one graphical representation of Clifford algebra and Grassmann algebras. Is that right? Because there are many works algebraizing graphs, for example. But I think we are going a different way. We want to get some graphical representation of that.
Yeah, well, yeah, it might well be that's right. She might be applying it in a completely incompatible way to the way I am trying to apply geometric algebras to graphs. But then I don't really, I think there must be much more close relationships. But, it's right. Well, that's the thing. Frobenius, what he did, again, off in a different direction for Frobenius inner product, which you can apply to as Dr. Page is relating now. So mathematics, of course, has exploded. And of course, no one person can understand everything that's going on. And some people are, like myself, are more limited than other people. But, each of us tries to understand what we understand in terms of what we're trying to understand. Well, physics, of course, theoretical physics, trying to understand, well, quantum mechanics, and has demanded more and more sophisticated mathematics, in which is, I hope, geometric algebras are supplying.
Well, these seminars are nominally fundamental problems in physics, right? So, in a sense, in the back of my mind, I'm thinking always about, well, what are the applications here? Like we're not talking purely about mathematics. We're talking about the kind of mathematics that has applications. Even if the mathematics is abstract, they have some application to understanding nature in some way or another. And geometry is, in a sense, one branch of mathematics that is obviously intended, for that. Like that was the whole point of geometry, was that it had a sort of physical intuition associated with it. But then what you're doing with Grassmann and compatible Grassmann algebras and so forth is hypothesizing that other algebraic structures more general than geometry, in a sense, like non-commutative geometries, or even things that are sort of pre-geometric in some way or another. These are sort of abstract algebras which potentially have application in physics. So, as you mentioned, like Frobenius algebras, like come up in things like topological quantum field theories and so forth, because the algebraic structure is saying something about physics.
Yeah, well, of course, our philosophies are, I think G.H. Hardy, gave the quote, the most important test in mathematics is whether it's beautiful or not. And he says, there's no room in mathematics for ugly mathematics, or something like that. But he was only interested in pure mathematics. He didn't want to do anything that was applied. But of course, later on, they discovered all kinds of stuff he was doing is applied. In fact, well, that's what they're finding about Grassmann algebra as well. For some reason, why has Grassmann algebra been slow in picking up? Well, but then mathematics has just exploded in all different directions.
So I think I do very much like your connection of looking at the relationship between Grassmann algebra and Clifford algebra. I think that's like very important direction, and in a sense, taking Clifford algebra away from its matrix representations is also very useful, and because it even though it might be kind of contrary to having intuition about what it means.
Well, I think it's very important reducing geometry to simple rules. I think Zbyszek would agree with that idea too, because that's the only thing we have for us to imagine higher dimensional spaces is rules, reducing geometry to rules which we can apply as well to higher dimensional spaces.
But when you make a claim, perhaps like Dr. Oshevich might make a claim like this, that really that all physics is really algebraic, right? That there's nothing in physics that that isn't essentially algebraic. So he would, like, that was clear from his earlier approach, say, to calculus and so forth. Like people would say, calculus involves limits, and limits necessarily are a geometric notion and so forth. But Ushevich started with a very different view, right? He's saying like calculus is really Leibniz algebras, algebra that 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 is extended in a way such that there's a new operation which follows the Leibniz axiom, and you haven't done anything geometric when you introduced that notion. You've just done something algebraic, which makes it kind of relevant to geometry, but you haven't enforced it. You've just made it
I'm not really
possible.
sure that there's no geometric interpretation of Leibniz rule as far as that goes. There's probably a way of thinking about that geometrically as well, but
Yes, but it's an abstraction from it, right? It's the rule without its intuition, but you choose such a rule because you know it has applications, right? Because you explore that kind of abstract structure, and
well, of
I
course,
don't
probably
know that.
the best idea there is the finite fields are exactly maybe a better example even than the Leibniz rules. A finite geometry, a finite field is, of course, very just abstract idea, but certainly can be used in geometry as well, of course. In fact, a bivector, people were arguing that bivectors really don't exist because of a finite field of 2 dimensions. So you can't have a bivector with a finite field mod 2.
Characteristic too, yeah. But the kind of extension that you're doing here with this notion of compatible Grassmann algebras, I think is one of those kind of ideas that has a connection to geometry, but isn't necessarily fundamentally geometric, right? In the same way that, say, adding a Leibniz rule to algebra doesn't make it necessarily geometric, but it allows you to express things which are relevant to geometry.
Okay, I can accept that. It's an interesting rule, of course, and the rules are very important in understanding anything. And I think it's an important, of course, it's a very important rule.
So when you introduce the notion of directed graphs and associating directed graphs, the edges of the directed graph with the with null vectors, you were presumably looking at that as a way of generalizing the notion of compatibility. Right? I mean, I think that's what you had in mind, like so that.
Yeah, that's right. So graph theory, you'd want a more general. I'm only considering with all pluses, the inner products of null vectors are all positive. But of course, that's a restriction. Depending on what you want to do,
theory
you don't
part
want that
of it,
restriction.
but the graph theory part of it is not deep, right? It's just a way of expressing compatibility in a more general way, right? That so that it's not so much that, at least I don't see in your work so far, applying Clifford algebra to graph theory, like not in that direction, but you're making use of the language of graph theory to define a more general notion of compatibility, which so in a sense that's why I think sort of the connection with graph theory and maybe even the connection with Platonic solids is a bit distracting to your original theme of understanding a more general notion of duality, right? of and how that possibly relates Clifford algebra backwards to, or back, I shouldn't say backwards necessarily, but viewing Grassmann algebras, compatible Grassmann algebras, as a representation of Clifford algebras. That's still, for me, that was sort of the starting point of your idea, and I like that direction.
Well,
but I'm not
as a
sure I
Chinese,
like these side issues seem a little distracting to me.
well,
from
as a Chinese like to say, let 1,000 roses bloom.
that. See, yeah, that's true. Okay, well, I'm not sure if we have anything else to talk about today. I'm not sure what your schedules are like over the next few weeks. Mine's a bit busy usually between Christmas and New Year's and so forth. So it would be natural for me, for example, if we were to take a break in our seminars and say continue in 4 weeks from today. I think, forget, I haven't really looked at what that would be. 4 weeks from today would put us sort of the middle of January, I guess. January
Okay, that would be fine.
11th or January 18th, perhaps.
Sounds fine with me. How about you, Dr. Cruz?
18, did you say? Mhm.
January 18th? Yes.
Okay, it's okay for me. Yes.
Okay. Should we, can we consider what subject we might address at that time on the 18th? Or I think, Dr. Cruz, you indicated that you had a paper that you were looking at you thought might be relevant to this subject.
Yes, because I am trying to, I catch the idea in this way. When we started using graph for representation of Grassmann algebra, this immediately take to me to the category theory, because I think that this graphical representation is a representation of the morphisms that we can build in that in that algebras. Then I am trying to organize some ideas around this in the way that we can understand this build of Grassmann algebras in terms of this construction of graph and related with category theory. This is the general idea. Then this paper I found have not a relation with category theory, but have relation with the graphs. And this, I think, is an important idea of how to get some representation of this kind of algebras. But I like to rewrite this presentation in terms of a more formal language of category theory. Then I kind trying to present these ideas to you in the next section. Mm-hmm.
Yeah, I think that would be excellent. I like the idea of involving category theory more deeply, And I think Dr. Sobczyk has mentioned on several occasions that he'd like the opportunity to understand more about how category
right,
theory might be applied.
So maybe, yeah, forward that paper you're talking about. We can study it a little bit ahead of time too.
Yes.
And then, all right,
I use
that's an excellent plan, I think. So we would meet next January next year, 2023. I guess that's January 18th, according to my calendar. And we'll have at least some introductory presentation by Dr. Cruz on the subject.
okay. Mhm.
Sounds good.
That's
So
okay.
Happy New Year and Merry Christmas.
Merry Christmas. Happy New Year. Yeah.
Yes. Okay. So have a good one, and we'll see you in about a month's time. Thanks.
Okay. Bye.
Bye.